Okay, let's continue the discussion. Let's talk about section 1.3. Complex numbers. Quadratic equations in the complex number systems. Okay, so in the quadratic equation solution part, remember that we have the quadratic formula. If you have ax squared plus bx plus c equal to 0, then x is going to be negative b plus minus square root of b squared minus 4ac over 2a. This is the root formula, provided if the discriminant b squared minus 4ac is greater than or equal to 0. And we know that if this quantity, the discriminant, is less than 0, there's no solution. Okay, so we want to solve it. The simplest example would be like this. If we want to solve this problem, we know that if you have arbitrary number x, its square can never be a negative number. So if this equation has no solution, then we don't know how to do that. So since it does not have a solution in our so-called real number system, we are going to create some new symbol to represent the solution of this equation. That's the origin of complex numbers. Remember that when we have x squared equal to 2, it has no integer solution. It has no integer solution. So we create a number square root of 2, and of course negative square root of 2. So this is a symbol. It's a symbol. It's not an integer solution. Actually, it's not even a rational number. But we just create it this way. And we know that we have a pi. Pi is an irrational number. What is the value? It's a 3.14159 stuff. But this is a symbol. We use this special symbol to represent that specific quantity. Here, we want to do the similar thing. We want to create a new symbol to represent the solution of this equation, x squared equal to negative 1. Okay, so that's our definition. The imaginary unit, which we denote by I, is the number whose square is negative 1. Okay, so I is the number, that new number, its square is equal to negative 1. That is I squared is equal to negative 1. Okay, so this is called the imaginary unit. So we do have a lot of expansions about the numbers. Whenever we cannot solve certain equations in the known system, number system, we are going to expand our number system, introduce more new numbers so that that equation has a solution. Okay, so that's the basic idea. But of course, those expansion should be done by the mathematicians, not by every people. If you expand the number system in this direction, the other person explain the number system in a different direction, then the mathematics will be so mess. So this is examined, this is reasoned by the famous mathematicians, not by us. Okay? Okay. Okay, so now we have I. I is called the imaginary unit. After the imaginary unit, let's see what is a complex number. Complex numbers are numbers of the form a plus bi, where a and b and a and b are real numbers. A and b are real numbers. And in this case, a is called the real part. Of a plus bi. And b is called the imaginary part of a plus bi. And I is an imaginary unit. Okay? And this is a plus bi is called standard form. Okay, so that's complex numbers. And if for the a plus bi, if b is equal to 0, so let's check the case. If b is equal to 0, then you only have a. 0 times I. 0 times every number is always 0. So then you will have only a. Then it is real. A is real. A, B are both real numbers. If A is 0, then you can directly write just bi. This is called a pure imaginary number. A pure imaginary number just means its real part is 0. Okay? So now we have a new number, a plus bi. So when the imaginary part is 0, it's just a real number. So in other words, we can say that all real numbers are complex numbers. All real numbers are complex. The imaginary part is just simply 0. And of course, not all complex numbers are real numbers because, for example, for this bi, it's not a real number. Okay? And once we have those complex numbers, we are going to study its addition, subtraction, multiplication, and division. Okay? So what is addition, subtraction, division, multiplication? To do that, we need certain identification. So first, two complex numbers are equal. So one number is equal to another number, if and only if the real part is equal to the real part and the imaginary part is equal to the imaginary part. You just compare the real and the imaginary part. Okay? So this is a identification. How do you identify a number? And second, if you have two complex numbers, so this sum represents one complex number. A plus bi, you represent one complex number. Usually you cannot simplify it. If a, b are both real, you can never simplify it. But if you try to add two complex numbers, you can only add the real part with the real part and the imaginary part with the imaginary part. This is addition. Okay? Real part plus real part, imaginary part plus imaginary part. And similarly, if you have a subtraction, you do the same thing. The real part minus real part, imaginary part minus imaginary part. So this is a subtraction. Okay, so let's just do one example. The example is simple because the rule is very simple. So assume if you have 3 plus 5i, this complex number, and plus negative 2 plus 3i. If we do addition, just add 3 and the negative 2, so you get 1. You add 5 with 3, you get 8. So that's 1 plus 8i, 1 plus 8i. And if you have a subtraction, 6 plus 4i minus 3 plus 2i. Remember subtraction. Subtraction, then 6 minus 3 is a 3. 4 minus 6 is negative 2. Negative 2i. Okay, so it's a 3 minus 2i. So 3 minus 2i, the real part is 3, imaginary part is negative 2. So here this a is a 3, this b is negative 2. So b and a both contain the sum. The sum between them is always plus, a plus bi. So b is negative 2, be careful. Okay, and next, after addition, subtraction, let's see the multiplication. Multiplication is the following. We just do term by term multiplication. So you have a times c, a times bd, a times di is a di, then bi times c and bci, bi times di, bdi square, I times I square. And we know that this I square is negative 1. That's the definition of I. So this becomes AC. And here, these two terms, you add them, if factor out I. AD plus BC, I. Here, I square is negative 1, so it's minus BD. So to summarize it, the real part is AC minus BD, and the imaginary part is AD plus BC times I. So this is addition, multiplication. This is multiplication. Of course, usually we don't memorize this formula. We just memorize the steps. So we do term by term multiplication. We do term by term multiplication. You will not memorize this as a formula. Because you see, for example, if you have 2 plus I times 1 minus I, what is the product? Product is just do term by term. 2 times 1 is 2. 2 times negative I minus 2i. I times 1, I. I times negative I is minus I squared. Negative sign I squared. Okay, so you got 2. Negative 2i plus I is minus I. I squared is negative 1. Minus negative 1 is plus 1. See? Usually you just do this computation. You don't memorize the formula because the formula is so close. You may get the wrong idea. You may get the wrong formula. So don't memorize this formula. Just memorize how do you do the computation. Term by term multiplication. Okay? Okay. In the complex numbers, there is a special definition, not appearing in the real case. So if you have a complex number z, a plus bi, assume you have a complex number, then its complex conjugate is defined as, okay, so we write like z bar. Z bar is called complex conjugate. Z is a plus bi. A plus bi bar. By definition is a minus bi. So you just change the sign of a bi, you get its so-called conjugate. Complex conjugate. Okay, complex conjugate. So for example, let's finish. Let's put the example. If you have 2 plus 3i, you put complex conjugate, it's just 2 minus 3i. And if you have a 6 minus 5i, you put complex conjugate, it's 6 plus 5i. You only change the sign of a I term. Okay? And surely we know that, you see, a plus bi. You change it, you get a minus bi. If you change it twice, it's a plus bi. Minus minus again becomes plus. So if you apply conjugate operation twice, you go back to the original function, original complex number. Okay? And with the complex conjugate, what is the advantage? Let's see, for example, why do we introduce this complex conjugate? Assume we have z equal to 3 plus 4i. Then z bar is 3 minus 4i. 3 plus 3 minus. And then let's see the product. Z times z bar. Three plus 4i times 3 minus 4i. It's just term by term. So 3 times 3, 9. 3 times negative 4i minus 12i. 4i times 3 plus 12i. 4i times negative 4i is a minus 16i squared. So I squared is negative 1. Again, it's negative 1. Negative 1 cancel with this negative sign, is plus. Negative 12i, positive 12i, they'll cancel. So it becomes 9 plus 16. So this negative sign will cancel this negative sign. So it's 25. Okay? So you see here, you have a complex number. You multiply it by its conjugate, then you get a real number. And this real number is the sum of squares, 3 squared plus 4 squared, 3 squared plus 4 squared. So this is an example. It gives us the following theorem. If z is a plus bi, then z bar is a minus bi, and z times z bar is equal to a squared plus b squared. That's exactly the computation. We just change 3 to be a, 4 to be b, you will get the same thing. Okay? So z times z bar is a squared plus b squared, is real. Is real. Right? It's very cool. Okay, so when it is real, let's see what can we do with this observation. For example, in the real numbers, we can find the reciprocal. And in the complex number, how do we find the reciprocal? In the standard form. For example, z is 3 plus 4i. Find z, 1 over z as in the standard form. Standard form means a plus bi. Okay, so how do we do that? We do the following thing. 1 over 3 plus 4i. we know that if the denominator is a sum, you cannot simplify it. If denominator has only one term, then we can do it. Now the idea is the following. We are going to multiply top and bottom by the complex conjugate of the denominator. Complex conjugate of the denominator. Now you see 3 plus 4i times 3 minus 4i. We just did the computation. It's a 25. It's a 3 square plus 4 square is 25. Enumerate, it's a 3 minus 4i. And in this case, we can do the division. It's a 3 over 25 minus 4 over 25, 4i over 25. The real part is the 3 over 25. Imagined part is negative 4 over 25. So this is the process to find the reciprocal. Okay, so and we can write the reciprocal as a standard form. Okay, if you understand this process, we can introduce the division among the complex numbers. So for example, if we have 1 plus 4i, 5 minus 12i, we want to compute the division of two complex numbers, not real. In this case, how do we do that? This is actually the division, 1 over it. Here is a 1 plus 4i over this. So we are going to multiply the top and the bottom by the complex conjugate of the denominator. In this case, it's a 5 plus 12i. And we know that z times z bar, the denominator, we only talk about denominator, z times z bar is equal to a squared plus b squared. A is 5, b is 12. So it is equal to 25 plus 12 squared is 144. This one. Let's put in the denominator. Okay, so that's why we get. That's how we get this 25 plus 144. It's 169. So the denominator becomes 169. And then for the numerator, it's a product of two complex numbers. So it's 1 times 5, 1 times 12i, 4i times 5, 4i times 12i. The denominator is 169. And if you practice a lot, you will directly write I squared as negative 1 and change it to be the minus. Okay. And this is a 32i over 169. And 5 minus 48 is a negative 43. And plus 32 over 169 times I. Okay, so this is the quotient of two complex numbers. So how did we do? We multiply top and bottom by the complex conjugate of the denominator. We write the denominator as a real number, and we multiply the numerator. And then we simplify the numerator and divide the real part by the denominator. Imaginary part by the denominator, and that's it. Okay, so do more examples and make sure you understand the computation. Okay. Complex conjugate. That complex conjugate is very useful when we have this fractional expression. And for the complex conjugate, let's see its own property. If your complex number is a real number, there's no b. No b means b is equal to 0. B is equal to 0 plus 0 minus 0 are the same. So if z is equal to a real, then z bar is equal to z is equal to a, because plus 0 minus 0 is still 0. So z bar is equal to z equal to a. So the complex conjugate of a real number is itself. So complex conjugation operation does not change a real number. It will change the complex number, but does not change the real number. Just keep in mind. And the second, we already mentioned that there's a theorem. We already mentioned that if you apply complex conjugate twice, you're back to the original. And also, if you have a sum of two complex numbers, you put the conjugate over the sum, it's equal to the, you distribute the complex conjugation to each complex number. And also for the product, you can distribute conjugation to each factor. And similarly, difference quotient applies. So let's put it here. This is different. Difference is correct. Complex conjugate also works very well with a quotient. Okay. So that's theoretical stuff. So we start from x squared equal to -1. We define I. We define the complex numbers, and then we know how to do the addition, subtraction, multiplication, divisions, and we know how to find the reciprocal. And then we, in order to define the division, we need the complex conjugate. We know that z times z bar is equal to the a squared plus b squared. It's real numbers. So there's so many steps here. And now let's study a little bit property of I. I, if you have only one copy of I, it is equal to I. And if you have I squared, we know that I squared by definition is negative I. And if you have I cubed is I squared times I. I squared is negative 1, so times I is negative I. Right? And then let's see I to 4. I to 4 is I squared times I squared. I squared is -1, and times -1 is equal to 1. So I to 4 becomes 1. And then let's check I to 5. I to 5 is I to 4 times I. I to 4 is 1, we just know it. So, and times I is I. I to 6 is I to 4 times I squared. I to 4 is 1, I squared is -1. But anyway, it is equal to I to I squared. I7 is I to 4 times I cubed. It's negative I. 8 is I to 4 times I to 4. It's 1. You will see that actually there is a pattern. It's repeated. The period is 4. I square 3, 4. This is a period. 5, 6, 7, 8. You see I -1. Negative I1, I -1, negative I and 1. And if you continue that, I to 9, it is definitely equal to I. I to 10 is equal to I squared, and so on. So there is a period. So the powers of I repeat every fourth power. The powers of I repeat every fourth power. And this is an interesting property. Based on this interesting property, we possibly have the following practice. For example, if I want to know what is the 27th power of I, how do we do that? We get the maximum multiple of 4. 27 is 24 plus 3. 24 is 4 times 6 and plus 3. It's 24 plus 3, 27. And then we know that every fourth power, the powers of I repeat. So this term, this 4 times 6 power of I is 1. So it's equal to I cubed. It's just equal to I cubed. This is repeated. It's like how you compute, how you check the weekday, Monday, Tuesday, Thursday. Every 7 days, it repeats. Here is every 4 powers, the power repeats. And if you have I to 101, it's I to 100. 100 is 4 times 25 and times I. For I to 4 times 25, this is repeated, so they disappear. So it is equal to I. And here is negative. I cubed is negative. Okay, so that's powers of I. After we get the powers of I, let's try some artificial computation. This is not a natural computation, just artificial. It is designed to help you to practice this result. 2 plus I cubed. For the algebra, we have several formulas. For example, 1, a plus b squared, a squared plus 2ab plus b squared, a minus b squared, a squared minus 2ab plus b squared. You already see this in the last video. And then the cubed, you have a cubed 3a squared b plus 3ab squared plus b cubed. And a minus b cubed is a cubed minus 3a squared b plus 3ab squared minus b cubed. Okay, so there are several formulas more or less like this. And there's another one is like a squared minus b squared is a plus b times a minus b. So this is another formula. So those formulas are important and fundamental in the study of pre-calculus and calculus. Okay, so back to our problem. 2 plus I cubed. It's this formula. So you get 2 cubed plus 3 times 2 squared, 4, and bi plus 3 times a is 2 times I squared and plus I cubed. Okay, now let's check. This is negative 1. This is negative I. So it's equal to 8 plus 3 times 4 is 12i minus 3 times 2 6 with negative minus 6 and minus I. 8 minus 6 is 2. 12i minus I is 11i. That's it. Okay. Okay, so that's a basic discussion of I and complex numbers. Now we try to use it to work out the quadratic polynomials. Before that, we only know that here x squared equal to negative 1, then x is equal to I. This is the starting point. And we want to expand it a little bit. For example, it's not negative 1, it's negative n. So if n is a positive real number, we define the principal square root of negative n, like negative 10, negative a million, denoted by square root of negative n as square root of negative n, square root of negative 10 is equal to square root of n, like square root of 10 times I. So we kind of separate n with I. We take square root of n and we take square root of negative 1. And again, this I is a imaginary unit. I squared is equal to negative 1. Okay, so for example, if we have square root of a negative 4, it's just 2 times I. 2 is the square root of 4. If we have a square root of a negative 8, it is equal to square root of 8 times I. Square root of 8 is 2 times square root of 2. Okay, so that's a little expansion of our discussion. First, we only discuss x squared equal to negative 1. Now we can discuss x squared equal to negative whatever number. So for example, again, we have x squared is equal to negative 9, not negative 1. X squared equal to negative 9, then x is, see, first we get principal, where's the principal square root? We take square root of negative 9. Whenever you have principal square root, you put plus or minus. Okay, and principal square root based on our formula is plus minus square root of 9 times I. Square root of 9 is 3, so it's a plus minus 3i. So this is the solution. This is the solution. Okay, is it cool? So it has 2 solutions also. Again, to solve it, we first find the principal square root, and then we put plus minus sign, because plus minus sign will be killed by the square operation. Okay, and in order to write down to simplify the principal square root, you follow this. So square root of negative 9 is square root of 9 times I. Square root of 9 is 3. So that's it. Okay, so after we understand this, we have our complete quadratic formula. For the ax squared plus bx plus c equal to 0, then x this has a solution given by x equal to negative b plus minus square root of a b squared minus 4ac over 2a. In this case, we don't say when b squared minus 4ac is negative, there's no solution. When b squared minus 4ac is negative, the remark. B squared minus 4ac is negative, then you are going to follow this strategy. Then it has 2 complex solutions. When b squared minus 4ac is equal to 0, it has a double solution. A double solution. Repeat it. X minus 1 times x minus 1. If b squared minus 4ac is strictly positive, it has 2 real solutions. Okay, so that's a complete, really complete discussion, but this discussion can only be complete after you introduce the complex numbers. Otherwise, this part is not complete. Okay, and this remark is on the page 110. On page 110, you will see the character of the solutions of a quadratic equations. Now let's see the example. When we have x squared minus 4x plus 8 equal to 0, let's assume we're looking for the complex, we're looking for the solutions in the complex system, complex number system. So what do? We follow it. So x is, denominator is 2a, a is 1, so denominator is 2. Negative b is negative 4, negative b is 4, plus or minus square root of b squared. Negative 4 squared is 16, minus 4a and c. Okay, b squared, this is b. So let me put it here. A is a 1, b is a negative 4, and c is 8 for this problem. Just always keep in mind, a, b, c has a sign, must include a sign. Okay, so it's a 4 plus or minus square root of 4 times 1 is 4 times 8 is 32. 16 minus 32 is negative 16. See? And then you have to explain what is a square root of a negative 16. So it's a 4 plus minus. It is equal to square root of 16 times I. Right? Based on this type of stuff. So you take the square root of the positive number and then put I. And 4 over 2 is 2. 4i over 2 is 2i. So it's equal to 2 plus minus 2i. So two solutions. 2 plus 2i and 2 minus 2i. What's that? Okay, 5. Okay, so that's a computation. And let's have the example for this remark. This is just application, and then let's see the remark. For the remark, A, you have 3x squared plus 4x and plus 5 equal to 0. If you have this solution, this quadratic equation, so A is a 3, B is a 4, and C is a 5. Then let's check the discriminant. B squared minus 4 is C. B squared is 16 minus 4 times A times C. Well, it's a 16 minus 60. 60, right? Yeah, 60. So it's negative 44, negative 44, less than 0, clearly less than 0. So it has two complex solutions. B. Second example, if we have a 2x squared plus 4x plus 1 equal to 0, then A is a 2, B is a 4, and C is a 1. And then B squared minus 4AC is 16 minus 4 times 2 times 1. 4 times 2 is 8, times 1 is 8. 16 minus 8 is 8, greater than 0. Then it means that this equation has two real solutions. Has two real solutions. And C, if we have 9x squared minus 6x plus 1, so A is a 9, and B is negative 6, and C is a 1, so B squared minus 4AC. B squared is negative 6 squared is a 36 minus 4AC. 4AC. It's exactly 0, so it has a double solution. a repeated solution. Okay. So that's the complete discussion of quadratic equations in the complex number system. Okay, so to summarize it, in this section is not long. In this section, we try to solve a problem. This type of equation has no solution in the real system. Because it has no solution in the real system, we introduce an imaginary unit. Imaginary unit corresponds to this one. Of course, -10 is not a unit. -1 is a complex, is a negative unit. So we start from here, we get I, and from I, we get a plus bi. And from a plus bi, we have addition, subtraction, multiplication, and division. Sorry. Yeah. We have those operations. And also, we have a minus bi, the conjugate. The conjugate times original function, original complex number is a squared plus b squared. So you go back and check the video. And then we study this square root of -10. Square root of -10 is square root of 10 times I. So you take square root. Square root is always directly computed for the real positive number. Negative number will negative sign will give you I. And from here we get the complete character of the quadratic formula. Two complex solutions, double solutions, double solution, double real solution. This is a real double real solution, or two different real solutions. So that's everything. Okay, so this section is over. We will start another video file to discuss the next section, maybe just part. Okay, we stop. Thank you.